Hi, this is Physics 1, Chapter 6, and this will be Work and Energy, Part 1. And we are looking at, I have two paints open. One second. There you go. I want to be able to see the time. These videos have shut off on me a couple times, and I have to redo the whole video when it happens. It happened like the last 3 times so far. The third time was a little different, but it just stopped. Okay, so we're going to look at work, and we're going to connect work with force, and then we're going to connect work with energy. So energy itself is connected to force. So things like thermal energy, in some instances, is connected to frictional force. Potential is going to be connected to gravitational, and this is going to be in the case of gravity potential, and it's going to be connected to spring force in the case of elastic potential. And then kinetic is connected to just like an applied force, and then like electric energy is connected to electrical force, and so on. Nuclear energy would be connected to nuclear forces. Alright, so work itself is a cross product between F and D, F being force, D being distance. Cross product meaning that the direction is going to matter. Now, one thing we can see here is that force and distance are proportional to work. So as the higher the force, the greater the work. So for instance, it's going to require this person here to lift more, to apply more force to lift a bigger box or a heavier box. Assuming the bigger one's the heavier one. It doesn't have to be, but in this case it will be. And the lighter weight doesn't require as much force for him to lift it. And so assuming that they lifted the same distances, this one's with more work is going to put in more energy to do that. Now, if we look at distance, let's just assume that these people apply the same force as they pull it back, but this person only pulls it back slightly and then like it lets go. It doesn't matter if this person pulled it back really hard with a lot of force, but only a little bit, it's not going to go far. I mean, you can try to do that, yank something back, but just don't yank it back that far and let go, and it's not going to go far. Slingshot, anything like that. This person, the farther they pull it back, the more energy they're putting into this, and so it's going to use that energy and use that work done to shoot out and go a lot farther, and have more energy to go a lot farther and move a lot faster. Right. So now let's get into the 3 possibilities you have when the forces are parallel to the motion. So force parallel to motion. And so when that happens, the work equals the force times distance. So in cases of parallel, we're talking, for instance, in this first one, you're pushing this, and it's moving to the right, and you're pushing to the right. You lift a object up, and it moves up. The opposite of this would be the force perpendicular to the motion, and the work will equal 0. One way to think about it is you lift up an object and you carry it. When you're carrying it, you did work to lift it up, but when you're carrying it, you're not doing any work. You're moving across the floor. The weight of the thing is down, and your motion is to the right, let's say, and so you're not doing any work. So you got zero work done. And then the third case is when you're pulling at an angle, kind of like in this picture. You pull this at an angle of 30 degrees. Part of this force is going to work because part of this force is in the X direction. And if you're pulling it to the right, you have part of the force that's pulling to the right. That part will do work. The other parts, perpendicular, that part won't do work. So we have to look at the part that is going to do work, and that's where we take the cosine of the angle. And so when force and motion are at an angle, the work equals force times distance times cosine of theta. Okay, so let's try these examples. First one, you're pushing to the right at a force of 100 newtons, and you push it 5 meters at constant speed. It's important to say this is a constant speed because if it's accelerating, then it's going to be a little bit of a difference of calculations. We would actually get into more calculus with that. So the constant speed helps make this stay algebra right now. Right, so work is going to be 100 times 5, and you get 500. And the force is in newtons, the 5 is in meters. So you get 500 Newton meters, and I kind of skipped this, but it's not much to say. 1 joule equals 1 Newton meter. Joule is going to be unit for work, for energy, for heat. So we can say 500 joules. The next one is, just say we're going to try this by raising a rope and having it pull at 30 degrees. The work is going to be 100 times 5 times cosine 30. And so we put this in the calculator. So 5 times 100 is 500 times cosine, and we check the mode. I knew it was going to switch back to me. Right, 30 degrees. And you have 433. It's 433 joules. And then the last one is we're lifting it up. Now in this case, the force, since you're lifting it up and you want to lift it at constant speed, you have to counter gravity. So your force is going to be your weight, mass times gravity, and then you're lifting it 5 meters. And so it would be 15 times 9.8 times 5. It's 735. And that'd be newtons. Oh, Newton meters, so joules. Alright, so lifting it up against gravity, ended up having the most. Now we can think of it this way. Let's say we only lifted it 1 meter just to get it off the ground. And so the work is going to be 15 times 9.8 times 1, which will be 15 times 9.8, be 147. So you get off the ground and then you move it 5 meters, and when you're moving it horizontally, you're not doing a work because it's going to be perpendicular to your weight. And so by moving it horizontally, you actually only do this amount of work to get it to the 5 meters, and then you just put it down. Alright, so let's do an example of this and combining different amounts of work being done. And this is going to be kind of a intense example, I guess you can say, or one with lots of parts. You just gotta kind of take it slowly. So this is a book laying down. This is a book on the bookshelf. And so you got one shelf, two shelves, three shelves. I think I state that there's going to be 4 shelves. And then we have the distances from the floor to the first shelf. Let's see, which is going to be 15 centimeters. So I'm going to kind of redraw this actually. So that's the floor. This first shelf is 15 centimeters from 0 centimeters. And the remaining shelves are each 38 centimeters above the previous one. So shelf 1 shelf, 2 shelves, 3 shelves, 4. And so 38 shelves above that, that would be 43, 53. And then plus 38, that would be, let's see, 83, 91. And 129. And that would be 4th shelf. So we have, actually, I think we have 5 shelves. Let's just do one more just in case we do get to the 5th shelf, which would be, let's see, 159, 167. Okay. So the book itself is, let's see, the book itself is 22 centimeters in height. Okay, so it's 22 centimeters long. And center of mass is going to be at 11. That's going to be important to know. All right. The average bookshelf holds 28 books. So we'll assume that we're going to put 28 books on each of these. And they're going to stand vertically, and the mass is 1.4 kilograms. How much work is required to fill all the shelves, assuming the books are all lying flat on the floor to the top? Alright, so what we have to do is we have to first find the energy, or the work I should say, to lift the book vertical. Okay, so basically rotating this book upwards. Okay, and the way we find this is that we are looking at just the work done to kind of move the center of mass up, so it's 11 centimeters off the ground. And so let's see here. So the work done here is going to be the mass times gravity of the book times the 11 centimeters, which I need a decimal. Okay, 11 centimeters. Okay, so that'd be 1.4 times 9.8 times 0.11. That's going to be 1.51 joules. Okay. we're not lifting it that high. They don't weigh that much. It's not going to be a whole lot of energy, but it will be energy we're going to have to use. And so we're going to have to flip these books and every one of these books. So we have to figure out how many books we're going to have. If we're going to put 28 on each of these shelves, and we have 5 shelves, we're going to have 140 books. So multiply this by 1.51. And so to flip or to rotate all books, we are looking at 211.4 joules. And that's the 1.5 times how many books we have. Okay, now that's just to flip them. And we're not flipping everyone, laying them on, having them stand on the ground like that. I mean, it's going to happen over time, but still, that's just to flip it. Now from this point, we have to look at where we place it. So each one is going to have a different amount. So for instance, the first shelf, you're only bringing it up. Yeah, I'm raising it from where the center mass is 11 centimeters to where the center mass is 11 centimeters above the 15 centimeter line, which will be 26. Well, 11 to 26 is 15 centimeters. So we're only raising it 15 centimeters. So for the first shelf, it's going to be the mass times gravity times the 15 centimeters times the 28 books. Okay, because we're lifting it 28. We're lifting all 28 books to the first shelf. And so we're going to want to get that total. Then the second shelf, it's going to be 28 books. Mass and gravity are the same, but you're lifting it from 11 centimeters to 64 centimeters, which is going to be a whole 53 centimeters. So we're lifting it 0.53. And the next third shelf is going to be 28 books, and you're lifting it 91 centimeters, so 0.91. Fourth shelf is the 28 books, and then we lift it 129 centimeters, so 1.29. And then the fifth shelf, 28 books, and we left it at 1.67 centimeters. Alright, so we'll do each of these, and then we're going to add all 6 things, and that will be our total energy. So 28 times 1.4 is the mass, times 9.8. Now I'll show you a quick way to do this. Alright, this is what we normally need, 384.16. That covers these first 3, so I can just use that each time. So we got 57.624, and then 0.53 times 384.16, and get 203.66048, and then 0.91 times 384.16, and you get 349.5856, and 1.29 times 384.16, and we get 495.5664. And then last one, 1.67 times 384.16. Wait, 641.5472. Alright, so let's start adding these. So plus 495.5664 plus 349.58. I think I missed the point. 0.5856 plus 203.604. It's not looking right. 48 plus 57.624, and then the last thing is the rotating the books, so plus 211.4, and you get 1,959.23 joules, because all of these are in joules. Okay, and it will take that much energy to do this. I put all these books on these bookshelves. Okay, notice to rotate them all, that took more energy than just putting them on the first bookshelf and just putting them on the second bookshelf. But putting them on the third bookshelf took more energy than rotating them. Alright. The next one, it's going to be more like an actual type problem you would see. This is a ramp problem too, which we've done ramp problems for forces. So you have a car, this is the angle, you have your mass coming down, you have a force pushing up, which would be, the engine, you have the normal force, and what you want to do is find the minimum work needed for a tow truck to pull a 950 kilogram car 710 meters up along a 9-degree incline. Alright. So one thing to know is minimum work. What that means is we're looking at a constant speed. Okay, it's going to take more work if we're looking at a accelerating the speed and increasing the speed as we go up. Alright, so only forces parallel to a line of motion does work. So all we want are the forces in our x direction. Okay, and if we switch our axis again, so this is y and this is x, that means the normal force is in the y direction and the pulling force is in the x direction, and part of the gravity force is in the x direction. So remember, this angle is going to be the angle from that vertical. So sine and cosine will be switched here. So you'll have, let me redraw this. You will have normal force up. We will have mg sine theta down the ramp, mg cosine theta across from the normal, and then the pulling force up. And so the pulling force minus mg sine theta, since we're not accelerating and we're doing constant speed, that has to equal 0. That means this pulling force must equal mg sine theta. Right? And so once you get the work, then you have to get, once you get the force, then you have to get the work. And the work is going to be the pulling force times times the distance. Okay, and the distance is that 710. So let's get the pulling force first. So FP equals, was the 950 kilograms times 9.8 times sine of 9 degrees. We get 14,000, or 1400, so 1456.4 newtons. Then we'll multiply that by the 710 meters, right? Yeah, and this will give us our joules, which is going to be a lot. So this is in joules, since it's Newton times meters. So I'm going to write it down here. So work equals 1034047.457. And then if we divide this by 1,000, we can get kilojoules, which is another common thing to put units in. I mean, technically we can get megnojoules, but it's just common to put in kilojoules. 1034.0 kilojoules. Okay, and so that's how you would do kind of a problem that actually will involve both force diagrams still, so that's not going away anytime soon, and as well as work being done. So we also have what's called the next thing, and this is going to be where we start to relate energy. And it's going to be called the work energy theorem. So I've mentioned a few times already through this, unless I mentioned the other video, I forgot to mention this one, because I've done this once and maybe a quarter. Alright, energy enables an object to do work. Right, energy is in joules just like work is. Work requires a force. Force requires acceleration. Acceleration includes a change in speed. Right, and so we have what's called the energy of motion, which we'll see as kinetic energy. Right, and this kinetic energy is going to be based on the speed. Okay, and think of kinetic energy goes directly with the speed. Now, if we're looking at two different instances of kinetic energy, so an object in this case speeding up, and they have speed 1 here, or slowing down for that matter, and they have a speed 2 there, there's going to be a change in kinetic energy, because they're going to have a kinetic energy here that I'll label as 1/2 mv1 squared and 1/2 mv2 squared. And so that change of kinetic energy is going to be 1/2 mv2 squared minus 1/2 mv1 squared. Okay. And usually what we do is we, instead of calling this, you can call it 2, but a lot of times we just call it the final and the initial. Okay, and if the initial is 0, then it just boils down to this equation. But you just kind of have to know what you're looking at there. And the work energy theorem is basically stated as work equals this change in kinetic energy. Okay, and this is actually very, very important and we kind of use it without even realizing we use it a lot of times, because just how we kind of start to do energy. But this is the foundation for it, and the foundation for why we would look at the change in kinetic energy. So we have a 3 kilogram object. It's dropped from 44.1 meters. The object hits the ground with a speed of 29.4 meters per second after 3 seconds. Show that this satisfies both kinematics and work energy theorem. Alright, so we're going to do it 2 times. One time using kinematics, one time using the work energy theorem. Then you can see that both ways work. You'll see that one is a lot easier actually, or a lot more preferred. Alright, so we're dropping. We're going to start with kinematics since we've learned that first. And we are dropping this 3 kilogram object. And so we're dropping it, so its initial speed is going to be equal to 0. And we're dropping it from 444.1 meters. Right, so let me kind of draw this out. So we're dropping out what this is, but I'll just make it round. And it's going to go 444.1 meters. And we know the acceleration is going to be gravity. I'm going to call down positive just so it makes it easier. So it's going to go down and hit the ground due to gravity. Object hits the ground with 29.4 meters per second. So final speed is 29.4 meters per second after 3 seconds. So time is 3 seconds. Alright, so let's start with a velocity equation. Right. Velocity at the final is 29.4. Initial is 0. Acceleration is 9.8. Time is 3. So 3 times 9.8 is 29.4. And so that checks out. And we get, if you don't believe me in that one, 9.8 times 3, 29.4. Okay. We also have one more kinematics equation. We're going to say y equals y sub 0 plus v sub 0 t plus 1/2 gt squared. Okay, it's plus because down is plus. Y sub 0 is going to be 0. Y itself is going to be 44.1. Velocity initial is going to be 0. That whole thing becomes 0. And so you have 1/2 gt squared. So 1/2 times 9.8, 3 squared has to equal 44.1. So I can do it on a calculator. 3 squared is 9 times 9.8 divided by 2. And you get 44.1. Okay, so that checks out. Okay, so now let's use the work energy theorem. I went backwards, but same thing. And we're going to start with this. We're going to start looking at the kinetic energy first at the beginning. And it's going to be 1/2 times 3 kilograms times 0 squared is going to be 0. Then the final, 1/2 times 3 kilograms times 29.4. That should be squared. times 3 divided by 2. And we get 1,296.54. Okay. Now, our change in our kinetic energy is going to be 1,294.54 minus 0. That'll be 1,296.54. Now we gotta find the work. And I don't mean to work by doing work equals kinetic energy, we're trying to prove that. But we want to find the work that's be force times distance. The force pulling down is mass times gravity. So that'd be 3 times 9.8. And then your distance is going to be 44.1. So 3 times 9.8 times 44.1, and we get the same thing. So we can say work equals change kinetic energy here. So it checks out. Right? So this should always be the case. The kinematics should work. The energy work theorem should work. What we're going to actually find is energy is a lot easier than kinematics a lot of times. Dive into this, understanding these things, and you can pick up on a lot of stuff, including help figure this stuff out. Okay, so I'm going to stop this video here. I'm glad I finally made it through a video. We're going to start going through the different types of energy and get into what's called mechanical energy, and soon we'll get into conservation of energy, and then we'll go from there. Okay, I'll see you next video.